Hello and welcome to another video. Okay, in this problem we're going to be doing majority element 2, and we're actually going to be learning a new algorithm called the Boyer-Moore voting algorithm. And this is probably the second time I've seen this algorithm, and the first time I've seen it I didn't really know the actual algorithm. I just knew kind of like the trick to solving the problem. So it is pretty rare, and honestly I'm not a huge fan of these kinds of things. But the reason we're going to go over it in this problem is because any other solution to this problem is basically an easy solution. So we're going to go through this, and this is not super complicated because let's just quickly mention like the easy solutions, right? So one easy solution is a sort, where you just sort and then you can just go like element by element and count up the number, and anytime an element appears more than n over 3 times, you would essentially add that into some array, right? So for example, we'd have like 2, 3, 3, and we need something to appear more than once, so we would say like, okay, 2 appears once, then we get a new number 3, and that appears twice, so we'll add 3 in there, and so on. So that's like an easy problem, not going to do that one. And the other one is obviously a hash map, which is also an easy problem. So we're going to go into this one, and we are going to first look at the case that is actually another problem. I think it's called majority element, actually, and kind of go over that one in a little bit more detail. So let's kind of simplify. I think the majority element asks you to find a number in an array that appears more than n over 2 times, and there's guaranteed to be an answer. So let's kind of walk through that and then get an intuition for how to build this n over 3. So let's just say we have an array like 1, 2, 3, 4, and then we just have like 5, 5, 5, 5, 5. That order doesn't actually matter here. So in fact, we can actually scrabble this up a little bit. So we could literally just go like 5, 1, 5, 2, 5, 3, 5, 4, 5, and this would also work. So in this problem, there are two different things that can happen. In the first majority element, I think they actually tell you there's guaranteed to be a solution, but in our case, there's not. So that's one trickier part, right? There is no guarantee that there is even a majority element, where in this one there is. So how does that change things? So let's actually go through this and let's see what happens if there is a majority element, kind of like what's the trick, and then we can figure out the intuition. So the trick for a majority element is actually pretty straightforward. You just go element by element, and you keep track of two things. You keep track of the element, let's call that L. We'll set it equal to, let's just say whatever, right? Let's say these are all positive, we'll set it equal to -1. And we will have a count. So we'll have a count, and it'll be 0. And essentially what you do is you just go element by element, and anytime you encounter an element that's different than yours, if the count was 0, you replace your element and make the count 1. Otherwise, you just decrement the count by 1. So let's kind of see what that looks like and show why this works and how it would fail. So for this case, let's say we start here. So obviously, and we made this like initial number something we can never reach. You can make it like -infinity if you want to. Okay. So we're going to go through this, and we encounter 5. So that's different than our previous element, and the count is 0, which means we've hit our case of we want to swap our element, right? So our element is going to be 5, and our count will be 1. Now we get a 1. That is different than our 5, but our count is not 0, so we don't swap. Instead, we just reduce the count by 1. So we reduce this to 0. Then we have a 5, and that's the same element, so we increase the count by 1, so it will be 1. Then we reduce to 0. Then we increase by 1. Then we reduce to 0, and you can kind of see like the pattern, right? So, and no matter how this happens, you're guaranteed to end up with the biggest element if you do this. Like the order doesn't matter. You can have 1, 2, 3, 4, 5, 5, 5, 5, whatever happens, because your majority element has count greater than everything else combined, you will get a solution here. So finally, we're end up with 1, and then this is our solution. But let's say we kind of change this up, right? So if we know there's a majority element, it's not that bad. We know there's only one array, pretty straightforward. But what if there isn't guaranteed to be a solution, right? Like let's say we actually redo all this work, but let's say that we're not guaranteed to have a solution. So actually, instead of this 5, like when there's guaranteed to be a solution, it's whatever your element is at the end, that's what you get. But what if this count, instead of 5, becomes 6, right? So what if we just change this to be a 6? And let's go through this one more time. So we get a 5, that's a new element, so we're going to put in 5 here with a count 1. And then I'm just going to quickly go through this, right? So this would make the count 0, then it would make it 1, then it would make it 0, then it would make it 1, 0, 1, 0. So after this element, the count is 0. And now when we go to this element, we've satisfied our condition of there's a new number and the count was 0, so we should replace it. But the problem is now, like, our final element isn't actually the majority, and there's no way to know that without actually going through this again. And your final element might be the answer, but there might not be an answer. There's two cases. Either the final element that you have here is the answer, or there is no answer. So how do we figure it out? Well, that's pretty straightforward. We would just loop back through array, and we have our element that we're looking for, and we just get a count here. So we would get a count of 1, and then we would see, okay, that's not more than half. So that's kind of the intuition. Let's kind of write this down. So for a n/2 solution. So n/2 solution, we just have an element. Every time the count is 0, replace it with a new one and make count 1. Every time you hit same element plus 1 to count, diff element -1 to count, unless the count is 0, right? So -1 to count, unless the count is 0, then you swap them. And then finally, whatever your final number is, get the count in the array. And there are two cases: A, answer is that, or B, no answer. And so the time complexity here would be O of n, because we would do a 2-pass solution, essentially. So now that we can recognize that with an array, for a majority element, there's either 1 or 0. Now let's think about if we have another array, right? And let's just make up some numbers here. Let's kind of do the same thing. And let's try to figure out, like, what are all the cases. And we can even show those cases. So if we have an element that we need to be greater than n/3, right? How many can we have? So let's say we have 9 numbers. Or it doesn't really matter, right? It doesn't really matter, because for 9 numbers you would need, so I'll just kind of figure out how many you need, right? So if we have 9 numbers, we need every element to be 4 or more, right? How many elements can be 4 or more total? Well, there can only be 2 maximum, right? Because one element has to be 4, another element has to be 4, there's only 1 left. Similarly, for something like 10, the floor divide is going to be also 3, so it's going to be 4 or more, so you need 4 or more, which is going to be, right, 4, 4, and 2, so there can only be 2. So for an n/3 solution, there can be 0, 1, or 2 elements that we can have. Just like for a n/2 solution, we can have 0, 1. Similarly, for n/4, we can even do that, right? So just to kind of show you how this would work for a generic case. So let's say we have n/4 solution and we have 9 elements. So n/4 floor divide would be 2. So we would need something to be 3. How many can you have? Well, you can only have 3, right? And so on. So for an n/4, there can be 0, 1, 2, 3. n/3, there's 0, whatever. So the general is there have to be whatever that you're dividing this 3 by, the answer has to be that number, right? So let's call this D, or whatever you divide by. Let's call this D. There can only be this answer, this like a result length, where this result length has to be less than or equal to D, right? So there can only be 0, 1, or 2 solutions. So we can't just like get 2 answers and necessarily assume that they are true, because like what if we just have, you know, let's say we have 9 numbers and we literally have like 0, 1, 2, or we just have like this, right? And let's say we keep track of 2 numbers, then our last 2 numbers will be something like 8, 9 or something, or maybe whatever, right? Whatever they are, but there's nothing here. So we kind of have to do the same thing. We kind of have to get like 2 possibilities, and then we have to go back and check that they actually exist. So let's show how we would do this for the n/3 solution, and then you can just apply this to like as many as you want from here on in. And it's going to be kind of the same process. So let's write down our steps. So we're going to initialize two numbers, set them to whatever that's not in the array. So I'll just set them to null, let's say. And then have count of each be 0. Then you go through your array just like we did last time. And we can have a few possibilities, right? So the main thing we want to think about is like, when do we actually decrement our numbers? Because before, whenever we had something that wasn't our number, we decremented, right? And the problem with that is like, if you just decrement like, yeah, let's say you have two numbers like 3 and 4, and anytime you get a number that's one of them but not the other, you decrement the other one, we'll have an issue. So if we have 3 and 4 and we get a 4 and we just say let's just decrement 3, the thing is we only use this decrement for potential replacements. So if we have a 3 and a 4 already, a 4 isn't a potential replacement because we already have a 4. So we will only decrement these when we get a number that's not either one of these. So let's write down our kind of like cases here. So A, let's say the number is our first number. So number equals first number. Then we just increment count of that, right? Then similarly, number equals second number, increment count of that. Let's get some more space. So this is kind of similar to our first solution, right? So those two are similar. Now let's go through our B case. So what about if the first count is 0, right? So we're getting a new number. So new number and first count is 0. So we're going to want to replace the first number first, and then we're going to want to replace the second number. So if this is the case, replace first number. But we don't want to decrement the second number here. We only want to replace the first one, and then that's it. So we're going to replace the first number and set count equals 1. And similarly, same thing. So let's say the first count wasn't 0, so same thing. New number and second count is 0. Replace second number and set count to 1. So essentially, if you have numbers to replace, if one of their counts is 0, you just replace them, but you don't decrement the count, and that's going to be important. And you can try that in your like edge cases, and you'll see if you replace one number but then decrement the count of the other one, that fails. So this is kind of our B. And then finally, we have our C, where new number and counts are both non-zero, right? So nothing to replace. Then we just decrement both counts. And then finally, we check for the validity of our result. So like I said, if you have something like 1, 2, 3, 4, 5, 6, 7, 8, 9, you're just going to have two random numbers in your result. And then once you go through your result, you're going to see that they don't actually work. So let's do this for a few different arrays and kind of like develop our intuition for this. And if you wanted to do this for 4, it would be the same thing, right? You'd have 3 numbers and 3 counts, and then you would do this exact same thing. If anyone can be replaced, you just replace. If they can all be decrement, you decrement, and you check the validity of every single one of your results. So if you wanted to do this for a generic case for whatever number you wanted, now you kind of have like a generic case where you can just plug in variables there. Okay. So let's go through some examples. Let's see if we can actually, I think these ones that they provide are a little small, so we're not gonna, yeah, they're a little small. So let's just go through some examples. So first of all, let's just go through like that 1, 2, 3, 4, 5, 6, 7, 8, 9 example, just to see what would happen there. And let's actually get rid of this, and let's try to have this fit, so then we can refer to this. Yeah. So say we go through our 1, 2, 3, 4, 5, 6, 7, 8, 9 example. Okay. Start over here. Our first number, we'll just write it over here. So our first number, we're going to make it null or negative infinity or whatever. Let's make it infinity. Second number, infinity. And our first count is going to be 0, and our second count is going to be 0. So we go to our number 1. Which case do we have? So this number is different than both of them. And so here, one of these can be replaced though, right? And remember, we're replacing the first number first. So we're just going to replace the first number with 1, and we are going to set the count equal to 1. Now for this one, can one of them be replaced? Yes. It's different than both of them again, so this gets replaced by 2, count equal to 1. Now here, nothing can be replaced, so we just decrement both counts. Now here, we replace the first one with a 4, make the count equal to 1. Now here, and we get a new number every time, right? So we replace this with a 5, new number 1, 6, decrement both. Nothing can be replaced. 7, this is replaceable now. So we replace 8, this is replaceable. Finally, 9, we decrement both counts to 0 again. And now our potential solutions are 7 and 8. So then we loop through our array and we get the count of 7 and 8. 7 only has 1, 8 only has 1, so clearly these don't work, so we just return an empty array. So that's what that would look like for something that fails. Now let's look for, same thing, 9 numbers, but only one solution. So let's look for, yeah, same thing, 9 numbers, but one solution. Let's just have one number be like 4 times maybe. So we'll have like 1, 2, then we'll have like 3, 4, 3, 5, 3, how many is that? 2, 4, 6, 7. Okay, then we have 6, 3. Something like that. So we have 1, 2, 3, 4, 5, 6, 7. We have 9 numbers, and 3 appears 4 times. So 3 should be our result technically. So let's kind of walk through this one more time and do this, and then we'll look at one with 2 results, and finally we'll call it there, and then we'll just code it up. So our first number will be whatever, right? Infinity. Second number, infinity. Our count for the first will be 0. Our count for the second will be 0. Okay. So the first number is replaceable, so we will replace it. Ooh, didn't notice that. I'm just gonna cross it out. So we're gonna replace it. Set the count equal to 1. Okay. Now we go to the second number. Now this is replaceable, and this is still a new number, so we will replace it, and we will set the count equal to 1. Now here for 3, we will decrease both of these to 0, so 0, 0. Okay. Now for 4, this is replaceable with a 4, and we will set the count equal to 1. So now we have this 3, and this 2 is replaceable with a 3, and we will set the count equal to 1. Now here for this 5, this is completely different, so we will set both of these equal to 0. Now 3, so we actually do have a 3, so remember if we do have a 3, we increment it. So we're going to increment this to 1. Then we have a 6, so we're going to replace this 4 with a 6, set that equal to 1, and then finally 3, we're going to increase the count of the 3. So now our 2 potential candidates are 6 and 3. When we get the count for 6, we only get 1, and then when we get the count for 3, we will get 4. So then 3 is actually valid, and we'll put that into the result. So that's what it would look like for a for one solution number. Yeah, let's just get rid of all this again. Okay. And let's do a 2 solution now. So once again, we'll use 9 numbers just to keep it simple, and we will use, or we'll say we'll have 10. So we can have like 4, 1, 4, 2, 3, 3, 3, 4. What's that? So it's 3 of each, and we'll have like 3, 4. This one's kind of a little clearer on like why it'll work, right? So we have 4 4s, we have 4 3s, and 1 2. Okay, and final one. So we'll have first, second, count, count. Okay. So we're just gonna, I'm not even gonna bother putting in the infinities because the first 2 numbers will just be replaced. So technically with these, if they're different, this will just go 4, 1, and then this will go 1, 1, right? They're just gonna be replaced. Okay, so now for 4, so now we have a 4, so we're gonna increase this to 2. Now we have a 2. This doesn't appear in any of them, so we're gonna decrease these to 0 and to 1. Now we have a 3. So this is replaceable, so we're gonna replace it with a 3, give it a 1. Now for 3, we're gonna increment, so this will be 2. Then we have another 3, we increment, it'll be 3. 4, we have a 4, let's increment. 3, we increment, and 4, we increment. So these are our 2 solutions, and then when we get the counts, we will get count 4, which is greater than 3, so those are both solutions. So that's kind of how you do this, and this is like the essentially, this is the algorithm that you use for your generic case. And it did delete double check your answers for the last part. Double check the possible answers because they could possibly not be, they could just be there but not actually be the answers. And this should be open. So now we have enough to code it up as what I talked about. So let's do that. So let's full screen. Okay. So we're going to make a first and second number. And I'm just going to make them null, but you can make them whatever, infinity. Anything that's not an array is fine. Then we're going to have a first count and a second count. So we're going to have first count. And you can even call this like something easier, but this is fine. Second count. We're going to make them 0, right? Because we want them to be replaceable right away. Then we go through our numbers. And then we want to make sure that we have our logic so that we have it in the right order. So obviously we can check if the number is one of the first, if the number is either first or second first, or if one, that's what we want to check first, right? If the number is one of the two, then we don't want to do anything else. So if num is first, that's the thing we want to check first. Then first count plus equals 1, and then we don't do anything afterwards. So else if, this is a bunch of ifs and else ifs. Num is second, we increment second count. Okay. So now we want to check for replaceability, because now if the number is not one of these, how do we know where, if we can replace it? It's by the count, right? So we want to replace first, so we're going to say else if first count is 0. Let's replace that one first. So first equals num, first count equals 1, else if second count equals 0, second equals num, and second count is 1. Yeah. Then we want our last case, right? And that means they're both not replaceable, so we'll just decrease their counts by 1. So first count minus equals 1, and second count minus equals 1. Okay, so now we have possible solutions in our first and second. Now we actually want to get their counts. So we're just going to reset their counts. You could do like a sum, but the problem is a sum would do a list comprehension, which does create additional space. So I'm not going to do that. So we're going to do first count, second count equals 0, 0. And we're just going to loop through our numbers and get the count here. So if num is first, let's increment first count. If num is second, let's increment second count. Okay. And then now we're going to make our result array. And we simply have to check if the first count and second counts are big enough. So if first count is greater than, and this is a floor divide, so we'll do length nums floor divide by 3. Then we can append the first element. Let's get a little bit more space. Same exact thing for the second element. So this is second count. Okay, and then finally we return the result with whatever valid or invalid. If these are valid, we'll put them in the result. Otherwise, we're gonna have an empty result. So we just return. And let's take a look. It's like accepted, and there we go. And yeah, I think most people have. There's basically only one solution here, so everyone should have roughly the same thing. Other than obviously a sort or a hash map. Like there's only really one way to do this, which is this. That's the only reason I could. Like if there was some super common algorithm to do this, I would definitely have gone with this. But I think I've described this one well enough to where you should be able to implement this in any. This can be any number you want now, in a generic case. And it's pretty rare, but you know it's okay. So for the time here, we are essentially looping through our numbers once, and then one more time. So that's O of n. And for the space, what did we create here? So we created these 4 things, which are just 4 local variables, and that is it. So, we also did create a result, which doesn't count, but even if it did, it only has 2 values max. But yeah, so this is going to be O1 space. And yeah, so hopefully that was helpful. Let me remember the name of this algorithm one more time. I'm never going to remember after this probably. So it's the Boyer Moore voting algorithm. And the next problem, you'll see this one is probably going to be in a year or when majority element 3 comes out. I don't know. So yeah, that's going to be it for this one though. And if you did like it, then please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.